consider a point A with position vector A with respect to the origin. Let vector B be any vector in space. Consider a line is passing through point A and parallel to vector B. Let us derive the equation for line L in vector form. Let P be any arbitrary point on line L. Let the position vector of point P with respect to the origin be vector R. Since the given line L is parallel to vector B, we can say that vector AP is also parallel to vector B. This implies that vector AP is equal to a scalar multiple of vector B. Let this be equation 1. Applying the triangle law of vector addition to triangle OPA, we get vector AP equal to vector R minus vector A. Let this be equation 2. Equating the values of vector AP from equations 1 and 2, we get equation 3. Equation 3 is the vector equation of a line that passes through a point with position vector A and is parallel to vector B. Now, let us derive the equation for line L in Cartesian form. Let the coordinates of point A be x1, y1, z1. Thus, we can write the position vector of point A as shown. Similarly, let the coordinates of point P be x, y, z. Thus, we can write the position vector of point P as shown. If the direction ratios of line L are given, we can find vector B that is parallel to line L as shown. Note that B is the direction ratio of line L along the y-axis and not the modulus of vector B. Also note that if vector B is given in its component form, then we can find the direction ratios of line L as shown. Substituting the values of vectors A, R and B from equations 4, 5 and 6 in equation 3, we get equation 7. Simplifying equation 7 and equating the coefficients of unit vectors I, j and k, we get the equations for x, y and z as shown. Eliminating lambda from the equations for x, y and z, we get equation 8, which is the Cartesian equation of a line that is parallel to a vector having direction ratios A, B, C and passes through points x1, y1, z1. If L, M and N are the direction cosines of the line, then the Cartesian equation of the line is of the form as shown. We can also determine the equation of line L if it passes through two given points. Let us first derive the equation for line L passing through two given points A and B in vector form. Let the position vectors of points A and B with respect to the origin be as shown. Let P be any arbitrary point on line L with position vector R. Since points A, B and P lie on the same line, vector AB and vector AP are collinear. This implies that vector AP is equal to the product of vector AB with a real number lambda. Let this be equation 1. Applying the triangle law of vector addition to triangle OAP and simplifying, we get the value of vector AP as shown in equation 2. Similarly, from triangle OAB, we get the value of vector AB as shown in equation 3. Substituting the values of vectors AP and AB from equations 2 and 3 in equation 1, we get equation 4. Equation 4 is the vector equation of a line that passes through 2 points with position vectors A and B. Now, let us derive the equation for line L in Cartesian form. Let the coordinates of point A be x1, y1, z1. Thus we can write the position vector of point A as shown. Similarly, if the coordinates of point B are x2, y2, z2, we can write the position vector of point B as shown. If the coordinates of point P are x, y, z, we can write the position vector of point P as shown. Substituting the values of vectors A, B, and R from equations 5, 6, and 7 in equation 4, we get equation 8. Simplifying equation 8, and equating the coefficients of unit vectors I, j, and k, we get the equations for x, y, and z as shown. Eliminating lambda from the equations for x, y, and z, we get equation 9, which is the Cartesian equation of a line that passes through 2 points with coordinates x1, y1, z1, and x2, y2, z2.